Alright, so now we are going to discuss the final family of organic compounds in general organic chemistry, and that is the carboxylic acids. And before we go on, because we're going to include the carboxylic acid derivatives, we go first with the carboxylic acids in themselves. And generally, carboxylic acids have this common functional group condensed as COOH, and in full detail, this COOH exists in this manner: C double bond to one O and then a single bond to an O, which is actually a hydroxyl group. So the name of this COOH is the carboxyl. Alright, now if you try to analyze, it could actually be derived from two functional groups. This is from the ketones and aldehydes, right? The carbonyl group. And this one is the hydroxyl functional group. Now, well, maybe what if we combine the carbo of carbonyl and the XYL of hydroxyl in order to come up with the name carboxyl? Makes sense, right? So we have here now a combination of the properties of the carbonyl group and the hydroxyl group. If you see here, the carbonyl and the hydroxyl in themselves both have oxygens, and what happens is that they make the carbon here very partially positive, and of course the oxygens here are partially negative. So that makes this carbon the site of attack for what? Since this is partially positive, will it be attacked by an electrophile or a nucleophile? Well, I think that's an easy question. It will now be attacked by a nucleophile. Alright, so usually nucleophiles attack carboxylic acids. Now, before we go to the reaction, let's discuss first what makes the carboxyl group so different that we call them acids. We know acids using the Bronsted-Lowry theory or definition as proton donors, right? They are proton donors, and practically this proton is here. So how did it come to be like that? So for example, let's draw the carboxyl group here. These ones have lone pairs, right? So the lone pairs could jump anytime, so we would be able to derive canonical structures, and we just play with this, and then it could jump to become something like this. It's just rotating, and in summary it will just look as if this pi bond here is rotating around the two oxygens. So what happens to the H here? The oxygens will be like, hey, we're so stabilized by resonance that we could freely release hydrogen anytime. And since this is proton donation, that makes it acidic. And since the resonance is strong, the capability to donate protons is strong, which makes it really acidic. In addition, since we have an OH here, we have a partial positive charge here, and we have a partial negative charge here. Carboxylic acid molecules can have inter and intramolecular hydrogen bonding. Let's say it's more sure to say that they perform intermolecular hydrogen bonding, or bonding with different molecules of the same type. Alright, now if that's the case, well, if we have a lot of hydrogen bonding, well, we could assume that they would also have high boiling points. Now let's go to the actual reaction mechanism. I said that we have here nucleophiles attacking a carboxylic acid, but there's kind of a difference. Maybe you would assume that they would undergo the same type of reaction as with aldehydes or ketones. So let's put here an aldehyde as a reference point. We know in the previous topic for carbonyl compounds that the reaction mechanism of aldehydes and ketones works in such a way that if I have a nucleophile here to attack the partially positive carbon here, what happens? The pi bond here is sacrificed, alright, in order to come up with something like this, in order to make the carbon give way for a bond with a nucleophile, because the C to H bond is nonpolar, therefore you cannot break that, right? Most especially if you have a ketone, alright, this is even less polar than that of a CH bond, so you cannot break that. You could only resort to break this one. But look at this, C to O bond, this is polar. What now if it's polar? Meaning that the OH could actually take away these electrons and act as a leaving group. And that is a better choice to give space for the nucleophile rather than breaking an actual pi bond. So here, if you're going to choose between this leaving group and this pi bond, it would be easier to break the bond for the leaving group rather than giving away the pi bond. So what happens is if the nucleophile attacks, the double bond is preserved, the pi bond remains intact, the leaving group, which is OH, goes away. Okay, it goes away as a byproduct, and the nucleophile takes the place of what used to be the OH here. So here, unlike this one, we have, for example, this aldehyde is A, this one is B. You have A plus B. You have AB. So this is addition. But here, let's say that the leaving group is B, the substrate is A, the nucleophile is C. So from AB, you added C, you produced AC plus B. So is this addition? No. Now this is obviously substitution. So if you think that carboxylic acids act by the mechanism of aldehydes or ketones, which is AN, you are wrong, because now we see that we are actually having the mechanism of carboxylic acids as nucleophilic, yes, but not addition, but substitution. And people or books further classify or name the SN of carboxylic acids as acyl, because it is true that you call this group here the acyl group. So you could say that this is acyl nucleophilic substitution, but that's just for formality's sake. So, but then again, remember this. Alright. Now, we have carboxylic acid derivatives. Alright. So this is the carboxylic acid as is. But, a carboxylic acid can be converted into some of its derivatives. First, let's have the carboxylic acid halide, where X can be chlorine or bromine or any halide. Now, the thing is, there is a difference among these derivatives in terms of reactivity and instability. Let's look at the structural effects. Let's try to see what structural effects exist. I'm going to use red ink. Now, in acid halides, halogens are very electronegative. What happens? They draw away the electrons. What happens? This one becomes a very, good leaving group. If it becomes a good leaving group, then it becomes highly susceptible for reaction by SN acyl. Alright? So, in reality, the acid halides are the most reactive of the carboxylic acids and carboxylic acid derivatives. Alright? Derivatives, I mean. Now, we call this an acid anhydride. So, it's 2 moles of acyl groups bonded by an O, and we say anhydride because as compared to carboxylic acid, this one used to be R C double bond O O H. The H has been removed and replaced by the acyl group. That's why anhydrous, removal of hydrogen. You remove this hydrogen to take this to replace this acyl group. Now for acid anhydrides, we have here oxygen. The same thing as with halogens, it draws away electrons. Furthermore, there's an additional hydrogen here which pulls away this these electrons from this carbon at the other side. What happens to this carbon? Carbon will be like, hey, I'm lacking in electrons. Hey, oxygen, can you give me? So what happens? Oxygen, which pulls electrons towards it, will be even deprived of more electrons by carbon. So oxygen here will be like, hey, this carbon is getting my electrons. So this carbon will have to give even more electrons. So acid anhydrides are actually also very reactive. They are the next most reactive derivatives to acid halides. Now the carboxylic acid, they have the oxygen, yes, they do have it, but unlike the acid anhydrides which have this additional partially positive carbon which makes this oxygen more unsatisfied, this oxygen only has hydrogen with it, so it has less problems. This is less reactive as compared to acid anhydrides. More especially this, we call this esters. This hydrogen does not give anything to the oxygen. Furthermore, this carbon even makes this oxygen less satisfied. This compromises the oxygen. But this R group, remember, R groups are carbons. They donate electrons to the oxygen, so it actually makes this more satisfied. So oxygen here would be like, hey, you know what, carbon, oxygen's like telling this carbon, hey, carbon, this R group is giving me electrons, so it's okay if you get your share of electrons. So as compared with carboxylic acids, esters are theoretically even less reactive than carboxylic acids due to the R's contributing effects to this oxygen. But usually carboxylic acids and esters are of the same reactivity. Now, here we have this group here, our RC double bond ONH2. We have here the amides. Okay, we have here an amide. Now, if the oxygen here has the capability to donate lone pairs to this carbon, remember that nitrogen is even less electronegative than oxygen, and nitrogen would even be more willing to donate to this carbon. So its capability to donate electrons to this carbon makes it very unreactive. It's very stable because nitrogen has no intention of being a good living group. It will stay as is. So meaning I've actually arranged it in order of decreasing reactivity. Most reactive, next most reactive, next most reactive, then the least reactive. Then we have I have a special derivative here, nitriles. I say special because look, they all have here the carbonyl groups. Only this one is the carboxylic acid derivative without the carbonyl group. But still, it's a derivative. Actually, this is the oxidized form of an amide, because it has this one is a single bond, this is a triple bond, so it's as if it's oxidized by adding more bonds between the carbon and nitrogen. Alright, so again, in order of decreasing reactivity, we go from left to right, then downwards. Now we go straight to the reactions, and I've actually summarized it because there's a lot of things going on at the same time. So I just want to say that first of all, if you have here acid halides, acid anhydrides, esters, and amides, you could all have them react with water. So I mark them all with green, meaning all of them could be added with water and it will all produce the same product, a carboxylic acid. And this process is known as hydrolysis, simply because you use hydro or water to make the reaction happen. Now, we go to other reactions. Let's go from the top downwards. For the acid anhydrides, for the acid halides, they can be converted into acid anhydrides, they could be converted into esters, they could be converted into amides, and they could be converted into carboxylic acids, meaning they could be converted into anything by several reagents. Now, from the acid halide to acid anhydride, you could use a certain reagent, all right, and the reagent that we're going to use here is simply a carboxylic acid. So you just give the RCOOH to produce this one, and the RCOOH here is actually this one. Alright, now next stop is from this carboxylic acid to acid halide. Actually, the only acid halide that we could produce from carboxylic acids, as given in the books, is an acid chloride, and we use a reagent containing chlorine, and that is this one. Remember this? We use this to turn an alcohol into an alkyl halide. Now we're going to use the same reagent, thionyl chloride, to convert a carboxylic acid into an acid halide. Alright, now we go to these 3 red arrows, meaning that it's all pointing to ester here. So we call this process, I'm going to code it in red, esterification, because you're forming an ester. So basically what you're going to do is you could use an acid halide, an acid anhydride, or a carboxylic acid. Then all you have to do is to add ROH, an alcohol. And where will the ROH manifest here in the ester? Actually, the RO here is the OR here, and the H is going to go somewhere else. Alright, now let's go to this asterisk here, and it came from the ester, and it points towards itself. So meaning from an ester you produce another ester. You call that transesterification. So basically you just use another alcohol different from the OR you used previously, and it will form an ester that's different from it. By the way, here in esterification you should use an acid, because that will serve as a catalyst, for example sulfuric acid or any kind of acid, as long as you have protons. Now the blue arrows represent formation of an amide. So you could, if you use ammonia, it will be called aminolysis. No, that's actually, if you use an amine, this is aminolysis, but if you use ammonia, you call this ammonolysis. Since here the product is NH2, the NH2 would come from ammonia actually, so this one specifically is ammonolysis. But the moment that it becomes something like NHR, it will be aminolysis, because the source will now be an NRH2 amine. Alright, and you use a certain reagent. This is DCC. Okay, the name is quite long, so I won't mention. I'll just mention the acronym DCC. Now I have a blank here. Remember I told you that nitriles are the oxidized forms of an amide. So we will go from a nitrile, then we will have it reduced by let's say a weak reducing agent such as sodium borohydride. So it will turn into an amide by virtue of reduction. And if we further reduce the amide, we will produce an amine. So the double bond to O will be reduced into carbon to hydrogen bonds. and we will form an amine. So basically, those are the playing reactions among carboxylic acid derivatives, other than oxidation reduction reactions. And that ends organic chemistry for carboxylic acids and for the basic families of organic compounds.